So in this video, we want to learn about the different types of clays. We want to learn what are one-to-one clays and what are two-to-one clays. Those are big groups that summarize clay mineralogy. And we want to reveal how exactly cation exchange capacity comes about in clay minerals. We want to learn about isomorphic substitution and edge charges as the mechanisms for cation exchange capacity. So let's start with the first example with kaolinite, which is one of the possible one-to-one clays, and a very common one at that. And for that we have a tetrahedral sheet, which is silicon surrounded by oxygen, and we have a dioctahedral sheet made up of aluminum surrounded by oxygen and hydroxyls. And on the figure on the right, you see how many of these layers of tetrahedral and octahedral units are stacking each other. And for kaolinite clays, you can see there can be quite a few of those, and it would take up to 3,000 of them to make a mineral that is 0.002 millimeters thick. Well, these layers stack with each other because of hydrogen bonds. So it's one joined to the other by hydrogen bonds. And we've already learned about those. And we know that these are really strong bonds, which means that nothing really can get in between these layers. So we have no water or any other ion getting in between these layers, which means that this particular clay, the kaolinite clay, is non-expanding. So water cannot get in between them and cannot swell the mineral. And it also means that this clay has no internal surface area. There is a lot of surface area. Just look at the image there and you'll see that compared to a sand or silt, this would have really high surface area. But there's no internal surface area between the individual stacks because the hydrogen bonds are holding it together. So in terms of clays, we say it has a really low specific surface area, and it's only in the order of 10 meters squared per gram. So now let's look at the cation exchange capacity for a kaolinite clay. The common chemical formula for kaolinite is Si4 aluminum 3 O10 and OH8. Well, the charges of those are 4 plus for the silicon, 3 plus for the aluminum, minus 2 for the oxygen, and minus 1 for the hydroxyl. So we add all these up, 4 positive charges and 4 silicon, 16 positive charges. For the aluminum, we get 12 positive charges. For 10 oxygen, each negative 2 charges, we get 20 negative charges. And for the hydroxyls, we get 8 negative charges, meaning that overall our kaolinite clay mineral is charged neutral, which would imply there is absolutely no cation exchange capacity. However, the kaolinite clay may have a cation exchange capacity because some of the charges on the edges may not be fulfilled at all times. So for our kaolinite mineral, we have the face and we have edges. And at the edge, we have our aluminum bonded to the rest of the mineral, bonded to hydroxyls, bonded to the silicon, and under pH neutral conditions, this structure would be charge neutral, just like we figured out. However, if we go to acidic conditions, so now we go into pH 5 or less, then we have more protons in solution, which means that the hydroxyls hanging off our aluminum may actually protonate. So they will accept an additional proton, which would then mean that rather having a charge neutral condition, we actually have a surface charge. So now we would have an anion exchange capacity. To get a cation exchange capacity, we would have to go to alkaline conditions. So let's say we have pH 8, and now our hydroxyls would, instead of protonating, they might deprotonate, meaning we have lost a proton here. And now we would have a negative surface charge, which would be a cation exchange capacity. So what we learned from this is that the cation exchange capacity for something like a kaolinite, which does not have a constant charge, is going to be pH dependent. If we are under acidic conditions, we would lose cation exchange capacity. Actually, we have anion exchange capacity. But under alkaline conditions, we would have a cation exchange capacity. Well, exchange capacity also would be relatively small. So overall, our kaolinite mineral, our one-to-one clay example, has really low exchange capacity, and whatever is there is pH dependent. And it's going to have cation exchange capacity under alkaline conditions. Well, the good news though is that little c, no internal surface area, not be absorbed by this clay mineral. It also means it's highly stable. It doesn't have any imperfections built into it. And this is what makes kaolinite perfect for making pottery and china with it. So we take the previous structure of one tetrahedral and one octahedral layer, and we replace two or more of the hydroxyls in the octahedral layer with oxygens. Then these oxygens can become the apical oxygens to join another tetrahedral layer to the octahedral sheet. So now we have a structure where we have two tetrahedral layers and sandwiched in between one octahedral layer, and that is what we call a 2-to-1 clay. Now if this clay is clean, meaning that we have silicon in the tetrahedral layer and aluminum in the octahedral layer, then this would be still a net neutral clay mineral that would only have cation or anion exchange on the edges, but would overall be charge neutral. And just like before, individual 2-to-1 units can join together with other 2-to-1 units, and here they would join with van der Waals forces. Now, a lot of times still, some of the elements in the tetrahedral layer and some on the octahedral layer get replaced with something else, and we call that an isomorphic substitution. So for the example that we have here, we would replace every fourth silicon item in the tetrahedral layers with an aluminum. Now the aluminum fits in there structurally the same as the silicon, which is why it is called an isomorphic substitution. But because the aluminum is only a 3+ and it's replacing what normally would have been a 4+ silicon, now we have a charge deficit of -1. And the muscovite might be represented by an illite if we have some more substitutions also in the octahedral layer. Both of these, muscovite and illite, are part of the mica group. And what's so unique about the mica group is that because we have this -1 charge difference, if we join together individual 2-to-1 layers, that charge difference can be perfectly satisfied by monovalent cations, such as potassium or sodium. And oftentimes it is potassium. Now, if the potassium gets in between there, that potassium is actually locked in place very, very tightly. And it's not really easily replaceable. So this does not contribute to cation exchange capacity. And as long as that potassium is in there, that also means that no other hydrated ion or water can get in between these layers, meaning that the mica group is not an expanding, so it does not have swell properties like some of the other clays. And the cation exchange capacity would be marginally larger than that of kaolinite. We continue substitutions in the tetrahedral sheet, where we now replace more of the silicon with aluminum. We come to minerals that are called clintonite or margarite, depending on the octahedral layer. Now, clintonite and margarite are sort of idealized because they're really clean isomorphic substitutions in the tetrahedral layer. But if the isomorphic substitutions are a little bit more varied, we will probably put these into the category of vermiculites. And here the main point is that most of the substitutions here happen within the tetrahedral layer. And because they are in the tetrahedral layer, the water molecules and exchangeable cations that are strongly absorbed within this interlayer space mean that these clays have only limited shrink swell potential. If, however, the substitutions are in the octahedral sheet, so here we might place a magnesium 2+ in the octahedral sheet in place of aluminum, we will come to a clay mineral that we will call montmorillonite. And montmorillonites are the most common member of a group of what we call smectites. And they derive their charge from the octahedral substitution of primarily magnesium for aluminum. The 2-to-1 layers in these smectites or montmorillonites are held together by van der Waals bonds and by relatively weak cation to oxygen bonds, which means that we have now exchangeable cations located between water molecules. They're hydrated in the inner layer, and that allows for expansion of the crystal lattice. So when a mineral is saturated with water, the spacing between the individual layers can approach 2 nanometers, which, if you remember, that's the size of a clay fraction particle. And then this expansion and contraction as the mineral dries down can often be quite problematic to engineers and farmers alike, because the soils would form cracks and they would be generally unstable. But a mineral like montmorillonite is a major constituent also in what's called bentonite, which is often used as a sealant in drilling application or as a seal layer in landfills. So to summarize it, we've looked at kaolinite as a representative of the 1-to-1 clay mineral group. In here we have one tetrahedral sheet and one octahedral sheet, giving it the name of 1-to-1. These sheets are held together by van der Waals bonds and by hydrogen bonding, which means that these relatively tight bonds restrict expansion and limit the reactive area to external surfaces. And isomorphic substitutions here in the kaolinite for silicon or for aluminum is pretty much negligible. So as such, the soils dominated by kaolinites, they have a low capacity for absorbing cations and have relatively low fertility. And the only fertility or cation exchange capacity that we would have these minerals is from the edge effects. So the joining then of 2 tetrahedral sheets, and one from each side, to one octahedral sheet produces a 3-sheet mineral type, which is called 2-to-1. And here we have this is represented as micas or illite, vermiculite, smectite, and eventually chlorite that we haven't talked about yet. The true micas or illites, they all have a relatively similar structure, where we have a substitution of aluminum for silicon in every 4th tetrahedral side. And that means that we have an excess of 1 negative charge per formula unit. And then this negative charge is satisfied by putting monovalent cations, which are mostly potassium, into the interlayer sides between the 2-to-1 layer units. And the interlayer cations then form a really strong bond between adjoining tetrahedral sheets, which means that these clays are not expanses. In most soils, these micas or illites are generally inherited from the parent material and occur in relatively unweathered state in the sand and silt fraction as well. And if you hike up Moscow Mountain, you probably will find some mica sheets there. So in the vermiculites, we have isomorphic substitution primarily in the tetrahedral sheet, which means that the magnesiums and calciums in their hydrated form that get in between the individual layers are relatively strongly absorbed within the interlayer space. And unlike the smectites, where the isomorphic substitution happens primarily in the octahedral sheet, the interlayer cations that are holding these layers together in the vermiculites are relatively strong, which limits expansion of the basal spacing, but doesn't quite exclude. So the smectites then are the ones that are the highly expansive soils. And the last group that we haven't talked about are the chlorites. And the unique thing about the chlorites is that we have an additional octahedral layer which fills the interspaces between the 2-to-1 layers and results then in the satisfaction of the excess charges. So of the minerals that we have in front of us, the vermiculite would be the one with the highest cation exchange capacity, followed by the smectite, the chlorite, illite, and kaolinite.